Here's the practice multiple choice quiz on gases. In question 1, did you catch that the Celsius temperature was tripling? With gas laws, you always need to use Kelvin as your temperature unit. Temperature and pressure are directly proportional, but only when the temperature is in Kelvin. So if I triple the Kelvin temperature, I would triple the amount of collisions, and that would triple the pressure. Same thing could be said if I had a flexible container. If I triple the Kelvin temperature, I would triple the volume, but not Celsius. So here the pressure will increase. We're increasing the temperature, but the pressure will not triple. And the only way we know that is just from lab data, that if I really go in the lab and I triple the Celsius temperature, it will not triple the pressure or the volume. Not when temperature is in Celsius. Question 2. Whenever we are given masses of gases, you're probably going to want to turn it into moles. Most gas properties are dependent on the number of particles, but not the identity of the particle. So I have 2 balloons at the same temperature and pressure. That's kind of important. So they're under the same conditions. One balloon has 14 grams of nitrogen gas, which is half a mole because nitrogen gas is N2 diatomic, and 20 grams of argon gas, which is about half a mole. Which of the following is true? The argon balloon will contain more particles? No, because that would refer to their moles. They have equal moles. The average kinetic energy of the nitrogen molecules is less than the average kinetic energy of the argon. No, average kinetic energy refers to temperature. On average, how fast are the particles moving? If they're at the same temperature, they have the same average kinetic energy. Volume of the balloons will be the same as long as the balloons are at the same temperature and pressure, and they are, in this case, same temperature and pressure. If they have equal number of particles, then they'll have the same number of collisions inside the balloon. And those same number of collisions will cause the balloons to expand to the same volume. So equal moles at the same temperature and pressure will give us equal volumes of gas. But the density doesn't have to be the same. So obviously, mass depends on the identity of the particle, and density is mass over volume. So yeah, in this case, the density of the argon sample is greater than the density of the nitrogen sample. It's more massive, but they have the same number of particles. It's just that the particles of argon are heavier than the particles of nitrogen. So they'll expand to the same volume, but the argon balloon might be more likely to sink in air, and maybe the nitrogen balloon would be lighter. Number of particles is always kind of important when we're looking at pressure, or it could be volume. This one is focusing on pressure in a closed container. So we've got this reaction happening in a closed container at constant temperature. So closed container probably means that it's something that maybe has a lid on it, or if it were a balloon, it's tied tightly so the number of particles cannot escape. Which of the following describes the change in pressure that will occur? All right, so I'm going from 4 moles of gas, total moles, down to 2 total moles of product. And so as long as the gas particles are at the same conditions, the pressure is dependent on the number of particles. So if I'm forming half as many particles, there'd be half as many collisions, so the pressure would go down by half. Doesn't matter the identity of the particle. We're concerned with the number of particles, or the moles. So I just looked at the coefficients in the balanced equation. 4 is easy, right? It's Boyle's law. Boyle's law looks at the relationship between volume and pressure. It's inversely proportional. If I have my highest pressures, I should see my lowest volumes. That's a good one. Number 5. This number, 22.4 liters, that is in your AP equation packet. It's kind of a constant. It's known as the molar volume of any gas at standard temperature and pressure. So you do have to be at STP, standard temperature and pressure. This 22.4 comes from Pervner, where if you plug in standard pressure, we'll leave volume as our variable. N would be 1 mole. R would just be the gas constant at whatever pressure unit you chose. And then T would be standard temperature, which the equation packet tells you standard temperature is 0 degrees Celsius or 273 Kelvin. And then they give you standard pressure, 1 atmosphere or 760 torr. If you plug those variables in, the units of STP, and solve for volume, you would get 22.4 liters. Regardless of the identity of the gas, it would just depend on the moles of gas. So if I had 1 mole of any gas, it should expand to the same volume under the same conditions. And under standard temperature and pressure, that volume would be 22.4 liters. So you can use that here. If you know you have 3 moles of any gas and you know it's at STP, multiply by 22.4 liters. Number 6, Pervnert. We have an unknown gas. The sample is 1.28 grams. We're given the temperature, the pressure, the volume, and we want the molar mass. And obviously we can use a calculator because this would be a little messy without one. Molar mass is something that people always forget, but it's a great way of identifying an unknown particle. Molar mass is grams per mole. So we know the mass, 1.28 grams, but we don't know the moles. And obviously we can't calculate moles because we don't know the identity of the gas. So that's what we'll use Pervnert for. So the only goofy thing about Pervnert is just that you have to be careful of your units. And so I have 1 atmosphere of pressure, which is going to determine the version of R I use. I'm going to want to use the version of R that's also in atmospheres so that these guys match. But then all of your other units do need to match the units on the gas constant R. So your volume must be in liters and your temperature must be in Kelvin. Then it's plug and chug. I can solve for moles, and then molar mass is grams per mole. Bingo, 168. Some more Pervnert. How many moles of gas would it take to fill an average man's lungs? If the capacity is 4.5 liters, I have a pressure of 760 torr, and I have to switch my temperature to Kelvin. Everything else is fine. I'm just going to use the other version of R. I want to make sure that these guys jive. I'm using the same version of R to match my pressure unit. Now, if you're solving for pressure, then, if it's a free response, then pick whatever version of R you want. And then just know that your pressure answer would come out in that unit. So I plug it all in, and I got about 0.18 moles. Now, with 8, you could take a little shortcut. So here's where that 22.4 is kind of handy. They give us this reaction. Aluminum reacts with hydrochloric acid. We produce a solution of aluminum chloride and hydrogen gas. How many grams of aluminum metal must be used to produce 33.6 liters of hydrogen at STP? That's the key, is that we're at standard temperature and pressure. So then I can use this guy. I can use this little equation right in here. And you can use it like a ratio. You can use it within stoichiometry. So I start with the 33.6 liters. Well, I don't want it in liters. Eventually, if I want to do stoichiometry, I need moles of hydrogen. Yeah, so then just flip that ratio. Cancel the 22.4 liters. I want it in moles. So we put moles on top. Now, if we stop right there, if I take 33.6 and divide by 22.4, I'm at 1.5 moles. So this much right here would give me 1.5 moles of hydrogen. Which now I just do the stoichiometry and it actually ends up being pretty manageable. 1.5 times 2 would be 3. 3 divided by 3 is 1. 1 times 27 is 27. 27 grams of aluminum. But we can take a nice little shortcut, and that's a great way to use the 22.4 liters per mole, the molar volume, as long as we know we're at STP. Number 9 was another one that was based on particles and moles. We had a 0.03 mole sample of solid ammonium nitrate that decomposes according to this equation. Well, the solid's not going to create pressure, so I don't really care about the solid, but the two products are gases. So I can look at the molar ratios to figure out how many moles of each gas are produced, and the total moles then of gas in the container. 0.09 total moles. If this reaction occurs in a closed 1 liter container at 400 Kelvin, which of the following is closest to the total pressure? So the total pressure is dependent on the total moles of particles. Now, this time I used the constant in atmospheres just because I noticed all the choices were in atmospheres. So I used the 0.08206 as my R and plugged in the 0.09 as my total moles. Number 10, under what conditions does a gas behave more like a real gas than an ideal gas? Well, ideal gases are not supposed to have significant intermolecular forces, but obviously real gases do. I mean, water can be in the vapor phase and it could still have some significant hydrogen bonds. It just depends on how close the particles become. And so, yeah, a real gas has intermolecular forces, and those intermolecular forces would become significant if the particles are close to each other. So at low temperatures or high pressures, because high pressures would create like a low volume, a smaller volume. If I'm forcing the particles to be closer to each other, then intermolecular forces can be more significant. Then, the fact that hydrogen is partially positive and oxygen is partially negative in a water molecule, that might cause those particles to be attracted to each other if I force them to be close enough. Ideal gases, then, are not supposed to have significant intermolecular forces. So we want to keep the particles away from each other if it's going to behave like an ideal gas. So what conditions might keep the particles away from each other? Well, the higher temperatures, the lower pressures, because that might create a larger volume. We could also add like maybe weaker intermolecular forces. If I had a nonpolar molecule, it's more likely to behave ideally than something polar like water vapor. So if I have a nonpolar molecule, it's going to have weak intermolecular forces to begin with, so they're probably less significant. Another thing that we might think about is having small moles. If I don't have a lot of gas particles in my container, well, then it's more likely that they can be a little bit farther away from each other and their intermolecular forces would not be significant. But if I have a lot of gas, then they just are forced to be kind of close to each other because there's a lot of particles in the container. Here's another cool setup with that Graham's law of effusion, where there's cotton balls soaked in 2 different solutions. When the solutions vaporize, their vapors will form a white solid. And we want to know which of these combinations would form the white solid closest to the center of the tube. Well, then they're moving at about the same speed, and they must then have about the same mass. So we're looking for the 2 particles that have nearly the same mass, or at least the closest masses. Number 12, a balloon is filled with hydrogen and a second balloon is filled with oxygen. The balloons have a volume of 1 liter at the same temperature and pressure. Equal volumes of gases at the same temperature and pressure will have the same number of particles. Here we're asked which of the following statements is false. So it's not the third one. The samples have the same number of particles. That is true. Even though they have the same number of particles, the particles have different masses. So the fourth statement is true. Oxygen would have a higher molar mass, which would give it a larger density. And then the other options. Average kinetic energy refers to temperature. So if the balloons are at the same temperature, then yes, they have the same average kinetic energy. But even though they have the same average kinetic energy, that doesn't always translate into the same speed or velocity. Now the heavier particles are going to move slower at a slower velocity. So no, the statement that's false is the first one. The particles will not have the same average velocity. That depends on mass. And the last few here. Which of the following gases will deviate most from ideal behavior? Sometimes this just becomes a matter of like, what on earth is the question asking? Ideal behavior means no significant intermolecular forces. And so if I kind of sketch most of them, I didn't sketch the helium, and I had to kind of play around with the SO2 a little bit and try out a few different types of bonds before I got 18 total electrons. Well, then I found that really the nitrogen and the CH4 are totally nonpolar. And so if they're nonpolar, they're just going to have weak London dispersion forces. And so if they have weaker intermolecular forces, they're more likely to be ideal. But the SO2 ends up being bent. It's got that extra electron pair on the central sulfur. Bent molecules are polar. So this guy's going to have dipole forces. So a little bit stronger intermolecular force, which then would make it deviate from ideal behavior. Weaker intermolecular forces would be less significant, more likely to act like an ideal gas. So that one I had to kind of sketch the SO2. 14 and 15 look at mole fraction. The concept of mole fraction is kind of like a percent. So if we want to know the mole fraction of neon in this mixture of gases, it just depends on the fraction of neon particles versus the total number of particles. So number of particles is going to refer to moles, which in 14, everything was in moles already. So I had 4 total moles of neon versus I added them up, about 25 total moles of gas for a mole fraction of 0.16. It's like a percent, but you don't have to multiply by 100. But it's like saying about 16% of the particles are neon, which then would mean that 16% of the collisions are coming from neon and 16% of the pressure comes from neon. So then just take that mole fraction, the 0.16, and multiply by your total pressure. And that's usually why we don't really multiply it by 100, because you're probably then going to take that fraction and multiply by the total pressure. So the total pressure is dependent on the total number of gas particles. So the fraction of pressure coming from a particular particle depends on the fraction of that particle in the total. Now you can also do mole fraction with pressure, because the pressure is dependent on the number of particles. So 15 sometimes kind of confuses people because they're like, how do I do mole fraction if I don't have moles? You can use pressure. So if I know that 250 torr are coming from the nitrogen, the total pressure was 890 torr, that ends up being about like 0.84. So it's about 84% of the pressure coming from nitrogen, which would have meant that 84% of the collisions came from nitrogen. So 84% of the particles, or the moles, were nitrogen. Those are great ways of using that concept of mole fraction. 16, this kind of comes from the lab. When you collect a gas by water displacement, you always have to do this little pressure correction. The total pressure is really the pressure of both the gas that you intended to collect and a little bit of water vapor, where some water molecules will evaporate off the surface of the liquid in your tube. And so we usually want to know just the pressure of the gas alone. And so you do this quick little correction. the total pressure will be given to you, as well as the vapor pressure of water at your given temperature. Water vapor pressures will increase depending on the water temperature. And so it's usually something that either you would look up on a chart, or in an AP question like this, they would just tell you. And then all I have to do is subtract off the pressure of the water. I want just the pressure of the gas alone. So often when we collect a gas by water displacement, we sometimes say that we had wet gas because it had water vapor mixed in. And so now we want to correct and solve for the pressure of the dry gas alone. All right, here's a couple questions that are really awesome, and they all refer to this data table. We have 4 gases, and they are all at the same temperature, 273 Kelvin. They're in 4 identical rigid containers. So identical containers would mean like same volume, and rigid would mean that like it's probably metal or glass. It's not a balloon. All right, so on the basis of the data, the gas in container 3 could be, so here's the deal. We have identical containers, which must mean that they have equal volumes. I could put that in here too. Identical containers would have the same volume. And they're at the same temperature. And I look on the table and they have about the same pressure. So equal volumes at the same temperature and pressure must contain the same number of particles. And so then the only mass and identity that we knew was the SO2. And so I just looked on the periodic table and took the molar mass of SO2, and shockingly, it is 64, which is 1 mole. So if these gases are in the same container, same temperature, same volume, same pressure, they must have the same number of particles. And now by looking at the mass of the SO4 and having it really be like 1 mole, I could say then that this 16 must also be 1 mole of gas 3. And so the gas that had a molar mass of 16 was the CH4. That's a cute question. I like these little guys. Same data under the given conditions. The average speed of the gas particles is, the speed or velocity depends on mass. And so the speed or velocity should be greatest in, whoopsies, not container 4, hello. They're asking me for the average speed of the particles is greatest in whatever particle is the least massive. And so if I look at helium versus neon, well, that's not hard. Helium is going to be only about 4 grams per mole. And neon is about 20. Oh, so the greatest speed, hello, should be container 1, the least massive. Brain fart. Got it. And finally, here's another good one. The best explanation for the lower pressure in container 4. So it's just a little bit less than the other 3 containers. But this was the same gas that I had to draw for a previous question. And it did end up being bent, which is polar. And all of the other ones are totally non-polar and would just have London forces. Whereas now this polar molecule is going to have a little bit stronger intermolecular force. So if the particles are a little bit more strongly attracted to each other, I might expect the pressure to be a little bit less. They're not going to collide maybe as often, or maybe they won't collide as forcefully if they're a little more attracted to each other. So the pressure was just a little bit less, probably due to the stronger intermolecular attractions. And then finally, here's the end. This little graph that shows the number of particles versus their speed. Which of the following graphs shows the speed distribution of the same molecules at a lower temperature? And that'll be shown by the dashed curve. So it is important to know that these are the same particles, so then they have the same mass, because that could affect the speed of the particles, right? So nope, it's the same, they have the same mass. So now their speed could be affected by temperature. Now if I increase the temperature, I'll increase the average kinetic energy, which as long as they're the same particle, it would make them move faster. And so we look at this little graph and we find the peak. That's the most particles in the sample, the majority of the particles in the sample, and if you were to follow it down, that would give you the average speed. Now there's always going to be some particles with more energy and some particles with less, but the peak is the majority of the particles, and then that would give you your average speed. So if I want a lower temperature, I want a lower average speed. So I'm going to look at the peak of the dashed graph, and I want it to be lower, at a lower speed than the peak of the original graph, which would give us the third one down.